8.2 Analysis Model. Isolated System. Energy. The outline of this video is as follows. We will begin by defining the isolated system model for energy. Then, we will discuss the important concept of the conservation of mechanical energy, which applies in specific cases. We will also look at what happens in isolated systems when non-conservative forces, like friction, are present. Finally, we will walk through 3 worked examples to see how these principles are applied. A ball in freefall, a theatrical problem involving an actor on a cable, and a spring-loaded pop gun. This slide introduces the concept of an isolated system, which is fundamental to energy analysis. An isolated system is one where no energy crosses the defined system boundary. This means there is no work, heat transfer, or radiation moving into or out of the system. In our main energy equation, this means all the energy transfer terms on the right side are set to 0. This does not mean nothing is happening. Instead, energy is simply transformed from one type to another, times within times the system. For example, potential energy can be transformed into kinetic energy, or kinetic energy into internal energy. The key takeaway is that for an isolated system, the total amount of energy it contains remains constant. Now let us look at a special but very common case called conservation of mechanical energy. This concept applies when we have an isolated system, which we just defined, and a second condition is met. Only conservative forces, such as gravity, are doing work inside times that system. In this situation, the change in kinetic energy plus the change in potential energy equals 0. We define the total mechanical energy of the system as the sum of its kinetic and potential energies. Since the total change is 0, we can say that the mechanical energy is conserved. This gives us a very powerful equation for problem solving. The final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy. Figure 8.2 provides a perfect example of conservation of mechanical energy. Here, we define our isolated system as the book times the Earth. When the book is held at rest at an initial height, y initial, the system has gravitational potential energy, but 0 kinetic energy. After the book is released and falls, that potential energy is transformed into kinetic energy. As the book's speed increases, its kinetic energy increases, while its height, and thus the system's potential energy, decrease. Because gravity is a conservative force, the total mechanical energy, which is the sum of the kinetic energy and the potential energy, remains constant at every point during the fall. We must also consider what happens when non-conservative forces, like friction, are present times inside times an isolated system. This is a common scenario, for example, a block sliding on a rough surface. In this case, mechanical energy is asterisk not times conserved. The non-conservative forces, because mechanical energy, such as kinetic energy, to be transformed into internal energy. You would observe this as an increase in temperature due to friction. However, the key principle of the isolated system still holds. The times total times energy of the system is still conserved. This gives us the most general statement for any isolated system. The change in kinetic energy plus the change in potential energy plus the change in internal energy must all sum to 0. This slide presents 2 quick quizzes to check our understanding. In the first, a rock of mass m and a rock of mass 2 meters are dropped from the same height. The second rock has twice the mass, so it starts with twice the gravitational potential energy. Since all of this potential energy is converted to kinetic energy at the ground, the second rock will hit the ground with twice the kinetic energy. The answer is A. In the second quiz, 3 identical balls are thrown from a roof with the same initial time speed, but at different angles. Because they all start with the same initial kinetic energy and the same initial potential energy, and they all end at the same final potential energy, the conservation of energy tells us they must all have the same final kinetic energy. Therefore, all three hit the ground with the same final speed. Let us apply these concepts to example 8.2, a ball in free fall. The problem asks for the speed of a ball, v final, at a height, y, after being dropped from rest at a height h. The first method involves defining our system as the ball plus times the earth. Because we are neglecting air resistance, this is an isolated system with only a conservative force, gravity, acting. Therefore, we can use the conservation of mechanical energy, which set the change in kinetic energy plus the change in gravitational potential energy equal to 0. The initial kinetic energy is 0, and the final is 1/2 m versus final squared. The change in potential energy is mgy final minus mgy initial. Substituting our variables, we get the quantity 1/2 m versus final squared minus 0, plus the quantity mgy minus mgh equals 0. Solving for versus final gives us the speed. V final equals the square root of the quantity 2 times g times the quantity h minus y. We can solve the same problem using a different approach. In this second method, we define the system as times only times the ball. Because the ball interacts with the Earth's gravity, which is now external time to our system, the system is non-isolated. The gravitational force does work on the system. We use the work kinetic energy theorem, which states that the change in kinetic energy equals the work done. The work done by gravity is the force, negative mg in the j direction, dotted with the displacement, the quantity y minus h in the j direction. This gives work equal to mg times the quantity h minus y. The change in kinetic energy is 1/2 m versus final squared. Setting them equal gives the exact same result. A what-if scenario shows that if the ball had an initial speed versus initial, that initial kinetic energy would be added inside the square root. This slide sets up a more complex problem. Example 8.3. An actor, with a mass of 65 kilograms, is attached to a cable that also holds a 130 kilogram sandbag. The actor swings down from an initial angle theta. Our goal is to find the maximum starting angle the actor can have so that the sandbag does not lift off the floor. The key insight is that the tension in the cable will be highest when the actor is at the very bottom of the swing. This is because the cable must support the actor's weight and times provide the centripetal force to keep him moving in a circle. This maximum tension is what might lift the sandbag. The first step in solving this multi-part problem is to find the actor's speed when he reaches the bottom of the swing. To do this, we will model the actor and the Earth as an isolated system. It is important to note that the tension from the cable is an external force, but it does no work on the actor, because the tension force is always perpendicular to the actor's direction of motion. This means our system is isolated in terms of energy, and we can use conservation of mechanical energy. The change in kinetic energy plus the change in gravitational potential energy equals 0. The actor starts from rest, so his initial kinetic energy is 0. We set the final potential energy at the bottom of the swing to 0. The actor's final speed squared is therefore equal to 2 times g times the initial height y initial. From the geometry of the swing, we can see this initial height is r minus r cosine theta, which simplifies our expression for the final speed squared. Now that we have an expression for the actor's speed at the bottom, we can move to step 2, finding the tension in the cable at that exact moment. For this step, we change our model. We now treat the actor as a particle under a net force. Looking at his free body diagram, 2 forces are acting on him: the upward tension from the cable and the downward force of gravity. Because he is moving in a circular path, he has an upward centripetal acceleration, which is equal to his final speed squared divided by the radius r. Using Newton's second law, the sum of forces in the y direction equals mass times acceleration. This gives us tension minus the actor's weight equals the actor's mass times the centripetal acceleration. We can solve this to find that the tension equals the actor's weight plus times the centripetal force. In the final step, we analyze the sandbag. We want to find the limiting condition right before the sandbag lifts off the floor. At this point, the sandbag is in equilibrium, and the normal force from the floor has just become zero. This means the upward tension in the cable is exactly equal to the sandbag's weight. Now we can combine all three steps. We take the tension equation from step 2 and substitute two values into it. First, we replace the tension T with the sandbag's weight, m_bag times g. Second, we replace the actor's final speed squared with the expression we found in step 1, 2 grams r times the quantity 1 minus cosine theta. This gives us one large equation. We can cancel g and r from all terms, and then solve for cosine theta. The result is that cosine theta equals the quantity 3 times the actor's mass minus the sandbag's mass, all divided by 2 times the actor's mass. Plugging in the given masses, we find cosine theta equals 0.500, which means the maximum angle is 60.0 degrees. Let us look at our final example, the spring-loaded pop gun. A 35-gram projectile is fired from a compressed spring. We have 3 states. State A is the initial position, where the projectile is at rest and the spring is compressed to negative 0.120 meters. State B is the equilibrium position, where the spring is relaxed, at y equals 0. State C is the final maximum height of 20.0 meters, where the projectile is again at rest. For this problem, we will define our system to include the projectile, the spring, and the earth. By neglecting air resistance, we can model this as an isolated system with no non-conservative forces. The key difference here is that we must account for types of potential energy: gravitational potential energy and elastic spring potential energy. This slide visually explains the energy transformations in the pop gun example. The bar charts show what is happening to the energy inside our isolated system, which includes the projectile, spring, and earth. In the initial state, before firing, the system has stored elastic potential energy in the compressed spring. It also has some gravitational potential energy because the projectile is below the zero reference point. When the projectile is at position B, the equilibrium point, the spring is relaxed, so the elastic potential energy is 0. We also define the gravitational potential energy to be 0 at this point. Therefore, at this instant, all the initial energy has been converted into the kinetic energy of the projectile. In part A of the problem, we need to find the spring constant, K. We can do this by applying the conservation of mechanical energy between the initial compressed state, which we call state A, and the final maximum height, state C. Our conservation equation is the change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy must all equal 0. We expand this to look at the final minus initial values for each energy type. At both state A and state C, the projectile is at rest, so the change in kinetic energy is 0. The change in gravitational potential energy is mgy final minus mgy initial. The change in elastic potential energy is 0 minus 1/2 kx squared, where x is the compression distance. We can then rearrange this equation to solve for the spring constant k. Plugging in the numbers, we find k equals 958 newtons per meter. For part B, we want to find the projectile's speed when it passes through the spring's equilibrium position, state B, where y equals 0. We will again use the conservation of mechanical energy, but this time between the initial state A and state B. The equation is the same. The change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy equals 0. This time, the final kinetic energy at state B is asterisk, not times 0. It is 1/2 m versus b squared. The final gravitational potential energy at state B is 0 by our definition. The final elastic potential energy is also 0 because the spring is relaxed. After substituting the initial and final energy values, we can solve the equation for the speed versus b. This gives a final speed of 19.8 meters per second. Let us summarize the key ideas from this section. We defined an isolated system as one with no energy, such as work or heat, crossing its boundary. For such a system, the total energy is always conserved. We then looked at a special case, the conservation of mechanical energy. This principle holds only if the isolated system has no non-conservative forces, like friction, acting within times it. In this case, the final kinetic plus potential energy equals the initial kinetic plus potential energy. If there are internal non-conservative forces, mechanical energy is asterisk, not times conserved, but the total times energy of the system is. The mechanical energy lost is transformed into internal energy. Finally, as we saw in the freefall example, our choice of system, whether it is the ball or the ball plus Earth, changes our analysis model, but it will always lead to the same correct physical result. This slide provides 2 review questions. The first question considers a pendulum. If the system is the pendulum and the Earth, we can use conservation of mechanical energy. However, air resistance is a non-conservative force that will eventually stop the pendulum. To account for this, we would have to use the full conservation of total energy equation, which includes a term for the change in internal energy, delta E int. The mechanical energy would be transformed into thermal energy in the air and the pendulum. The second question asks us to recalculate the maximum angle for the actor in example 8.3, but with a new mass of 70 kilograms. Using the same formula we derived, cosine theta equals the quantity 3 times the actor's mass minus the sandbag's mass, all divided by 2 times the actor's mass. This would give a new, larger maximum angle.